Okay. So can someone tell me as to what we were discussing in the previous class? Rohit P.
Uh, so we had learned the sums for that max terms and min terms, sir.
Okay, good.
And then you're about to explain generation of switching equations from truth table.
Exactly. So we are going to now look into, thank you, Rohit. So now we are going to look into how to extract more information with the data that we have. Okay, how we are going to go about getting the equation. We have already seen that with an example, but we will dive in deep and we will see as to how exactly it can be done. Okay, right. So just let me get the materials. So this was the flow chart, that I was about to start. Okay. So before we move forward, I want the feedback from all of you. Okay, how is this class going so far, or um, how are you feeling with the digital electronic circuits class? I want your honest feedback so that if any changes, I can incorporate them. Please feel free to give me your feedback, so that if necessary, I can make some changes.
Sir, it would be better if you could send notes. Like
Mm,
if
mm,
you're teaching some part today, you could send that part's notes the
mm,
same day.
mm.
Because sometimes your videos doesn't open, so there's a problem with it.
Is it?
Yeah, and then
Video?
during class we can't complete like everything what you're showing on the screen. So
Mm,
little bit of notes would be helpful.
okay, fine. So today, what I will do is I will upload the whole modules notes itself. Okay, or I will just look into as to how I can get things done. And yeah, at least in what we have covered so far, I will try to share them. That shouldn't be a problem. Apart from that, anything else that you would like to tell me? Any other feedback that you guys would like to give me?
No, sir. No.
Okay, fine. So all of you are following, right? It's not difficult for you to follow whatever I'm explaining, is it? Supriya,
Yes, sir. We
Supriya.
can follow.
Okay, thank you, Bhargav. Supriya, you're able to follow? And one thing that you all can keep in mind is, since this is an online class, okay, as I told you previously, self-discipline is very much needed. So when I say self-discipline, okay, you have to make sure that you are in sync, okay, you are managing time, you are getting your doubts clarified, okay. So those things you should probably look into. And if any doubts, yes, some of you have started asking me doubts, which is a good thing, right? So even I feel good when you guys ask me doubts, so that I can revisit them and explain it back to you, okay, which is a good thing. Fine. So let's continue with our discussions, and we will see as to how we can generate this switching equations, which is in the flow chart. Okay, so this is a process. The whole thing is a process. My ultimate thing is to build a circuit. So how do I build a circuit? There are a series of things that needs to be done. Number one, number two, number three. So we are somewhere now at number three. Okay, where we will generate equations. So once these equations are generated, as usual, I do not want a complicated equation. I will want a simplified version of it. So I'll get it as simple as possible. Then I draw a diagram for that. I verify if it's proper or not. Then I go ahead with the circuit. Simple, right? Okay. So now we will get into the generation, and we will see as to how we go about doing these things. So these problems were discussed in the previous class, and conversions, taking complement. Okay. Switching equations or Boolean function. You can make note of this heading: generation of switching equations from truth table. Okay. Switching equations or Boolean function can be written more conveniently by using the minterm or maximum. Now we are very clear with this. Any truth table given to us, we can either pick up ones and say that these are the minterms, or we can pick up zeros and say these are the max terms. Minterms with lowercase m, max terms with uppercase m, and I'm picking up zeros wherever there are zeros at my output function f for whatever is my input combination, xyz or abc, okay, or jkl, whatever can be your input combination. Okay, I am interested in looking into my output functions, which is f. Okay, summation is used for midterm, and your pi is used for max terms. These things should always be in your mind. Below example, we will see how we generate switching equations. Fine. Now there is a problem given. Now as I told you, first we will have a problem statement. So after problem statement, what is it? Someone tell me after problem statement in the flow chart. Stanley, I think now you can answer. Stanley there? Yes, Stanley, go ahead. Tell me after problem statement, what is next?
So truth table.
Okay, fine. So we have to generate ones and zeros. So if I have to generate ones and zeros, I have to generate a truth table. I have to make sure that I put all these ones and zeros in order, and you know fill up my truth table. So first is our problem here. Okay, so which states a majority gate is a digital circuit whose output is equal to 1 if the majority of the inputs are 1. So you're getting it, right? If, say, we have three inputs, x, y, and z. So if x and y are 1, okay, so out of 3, if 2 are high, then I'm going to give the output function as 1. So this is my problem statement. If there are more number of ones, output is 1. If there are less number of ones, output is 0, right? So that's what it means till here. the output is 0 otherwise. Okay, so which I have told you guys already, output is 0 otherwise. By means of a truth table, find the Boolean function implemented by a 3-input majority gate. So this majority gate checks for the number of ones, if the number of ones are more or the number of ones less. So if less 0, if more 1. Simplify the function. Okay, so we have a problem statement, and then just for my understanding I try to draw a block diagram. I say that x, y, z are my inputs. This is my majority gate. I consider it as a black box. What's a black box, by the way? Can someone tell me what's a black box?
Sir, can you repeat it once?
What is a black box?
Sir, it's the recorder in an aeroplane, no, sir? Like
Yes,
it records all the
that is
communication that happens.
correct. That is also a kind of black box. But here in our circuit, when I say a black box, which means there is some circuit inside. Okay, and I'm really not bothered what the circuit does. Okay, how is the circuit connected? I'm not bothered, but I will only worry about what it is doing. Okay, so we can in general call it as a black box. Okay, anything for that matter. I'm not worried as to how the connections are going about internally, but I will just say, this is my box and the box name is majority bit. So we can call this as a black box. And sign, yes, that's also a black box where recordings happen between pilots and co-pilots, and in case of emergency, this black box is retrieved and they try to investigate based on the information stored in the black box. Okay? That is also called a black box. So here in our circuit world, okay, in electronics, we call this any block diagram, okay, which I'm not interested in knowing what is internally present and how it is connected. I just call it as a black box. Okay. So x, y, z, I take them as my inputs, and my majority gate and my function f as the output. Right. So since I know it's a 3-input function, I know that I have to start from 3 zeros to 3 ones. Right. So 0, 0, 0 up till 1, 1, 1. Now f is not given to us. Now we have to generate this f. How do I generate this f? I have to take the problem statement. Now in the problem statement, it is telling me that the output, which means f is high only if the ones are majority. When will the ones be majority? Let us take them one by one. So here, is there any ones? No. So I take it as 0. Here there are ones, okay, but majority is what? 0. I have 2 zeros versus 1 0. So it's 0. Similar case here, but here the case reverses. I have just 1 0 and 2 ones. So majority of bits, with majority of high bits is high. Okay, majority of ones. So I take my output as 1. Similarly here, zeros are more than ones. So 0, 1, 1, 1. Is this concept clear? How we are getting the truth table? Students, I want you to respond, be active. Yes. Is the truth table clear?
Yes, sir.
Yes. Fine. So we are taking function f is equal to 1 when we have more number of ones in your combination x, y, and z. Right? Next, now we will go with our equation. So f is a function of x, y, z is equal to summation. Now when I say summation, what does it mean? Does it mean min term or max term? Yes, exactly, it's a min term. So what I do, I see for ones. So ones is at 2 plus 1 3, so 3, then 4 plus 1 5, okay, then 4 plus 2 6, and then 4 5 6 7. So this is my equation now. I understood what is the problem. I drew the truth table. From the truth table I'm writing the equation. Okay, now if I have to write the max term, then it's going to be reverse of 3 5 6 7, which means I'm going to leave out these numbers and pick up the other ones and represent it as pi. So 0 1 2, 3 is here, 4, 5, 6, 7. Okay, 5, 6, 7 is here. I leave them out. So 0, 1, 2, 4. This is going to be my max terms. Okay. So if I have to represent them, okay, this is how I'm going to represent them. 0 means I don't have a bar. Right? 1, I have a bar at Z. Okay. 2, I have a bar at Y. 4, I have a bar at X. Okay. And okay, for this one, okay, for our min terms, it's going to be the reverse, right? Y and Z is high, okay, so that is my 3. Y bar is low, so it is 4 plus 1, which is 5, okay. Similarly 6 and 7. Till here, guys, do you have any doubt how we generated min terms and max terms? Any doubt? Please tell me. Any doubts so far? Any doubts so far? So can I proceed? Okay. Cyan, am I audible now? Okay, there was a power outage. So, yeah. So, any doubts still here now? How we have generated min terms and max terms? Any doubts here as to how we generated these um, equations? Fine. So, we have min terms here. Thank you, Cyan. And we have max terms also here. Okay. So, this is how we go about generating. And not only having these equations, we will even get them simplified. Okay. So, I take them as x bar y z. Okay, I am rearranging them x y z plus x y bar z. Okay, and yeah, x y z. Okay, I can even repeat them if needed. Okay, and x y bar z, x y z bar plus x y z. So I can take things common now. Now remember, keep in mind, okay, this is just like your algebra. You can play however you want to. If you want to reduce, you can increase the terms here, take them in common. Okay. The reason why I'm doing this is because I get x bar here, I get y z here as common. Okay, so x and x bar can be eliminated. Okay, and similarly here I can take x and z as common. Okay, and my y bar, okay, can be eliminated. So similarly here I can take x y as common, and z and z bar can be eliminated. Now see this equation here. Okay, x y bar z. Okay, it's I 1 2 3 4 4 terms with x y and z, and I'm going the reverse process. Actually, I'm converting them back. Now again, if you want to increase this, okay, if you want to increase this, what we normally used to do is, since there is no x here, okay, we take x and x bar, right? There's no y here, so I take y and y bar. Okay, there's no z here, I take z and z bar. So you're understanding the process, right? If we want to increase, we take them. If we want to decrease, then we can repeat those terms. Okay, we can repeat those terms, take common and get a final equation. So here I rearrange them, I put them as xy, yz and xz. Okay, so I have a problem here. I understand what is the problem. Uh, it's not needed that you draw this block diagram, okay, but it makes our understanding more simpler. Okay, then you can have this truth table. So as soon as you get the truth table, okay, you
Sir, I
can,
have a doubt here.
yes, please go ahead.
Sir, the
Ah,
equation that you wrote
ah,
for the midterm,
ah,
that is x bar y z plus x y bar z, and then
mm,
y z bar plus x y z. That is
mm,
okay. But in the next line, how we
mm.
are getting two extras x y z?
Yeah, that's what I'm telling. If we want, we can take extra. Okay, like how we are eliminating extra, we can take extra for the purpose of grouping. I want to group them.
Okay.
Huh? So how will I group them? Only if
Okay,
I
sir.
have extra. So in our previous, what we see, it's like this reverse engineering. Are you guys aware of reverse engineering? Leave this subject. Okay. Now let's talk about reverse engineering. What is reverse engineering? Is this term familiar to all of you? I need some response. Is reverse engineering familiar to all of you?
Heard of it, sir. Heard of it.
Huh? Yes? Bhargav, I didn't get you there. Okay, heard of it. Fine. So in reverse engineering, what happens is I have a complete product. Okay. And I want to know what is the circuit. So what I do, I take the black box. Okay. I say a black box because I don't know what is it inside. So I take the finished product and then I try to, you know, remove, okay, whatever possible, and then I go to the root level, which is the circuit level, and then I understand how the circuit is connected. So I'm going in a reverse process instead of actually going in a forward process. How do I go in forward process? I see the problem statement, I build, I generate the truth table. Once I have the truth table, then I generate equations, simplify equations, I draw the diagram, then go with the circuit, right? But here in this case, what am I doing? I'm getting a finished product and then I'm trying to open it up and trying to check as to what exactly is inside. So this is reverse engineering. Similar concept can be applied here also. Okay, since for the purpose of grouping, okay, I want to group x bar with x, okay, so that y and z becomes common. Now the reason why we have taken this is because for grouping. So if I can group them, then I can reduce them, right? So previously what we used to do, whenever there used to be two terms, we used to take one term, right? So here we can also go the reverse way. If there is just one term, we can take the other term. It is not going to affect the value of the function. Okay, the value of function is not affected at all. So I take these extra terms, group them and reduce to my final simplified equation. So is that clear? Is that clear, Nirmit? Nirmit, is that clear? You can also use the chat box if you are unable to unmute. Or so students, you understood whatever I have told so far, how we generated this equation? Yes, please give me a confirmation. Yes, we have a question there. Sir, can you explain 3, 5, 6, 7? Okay, so how is this 3, 5, 6, 7? Yeah, Okay, so consider this equation here. Okay, now since this is in what format? Min-term format. So min-term format, I have told you, do we consider 1 or 0? We consider 1, right? When I say 1, there shouldn't be a bar. So here y and z does not have a bar. Okay, so if it does not have a bar, then I consider it as high. So it is like writing 0, 1, 1. Okay, and the next one, so what is 0, 1, 1? 0, 1, 1 is nothing but 3, right? And then 0, sorry, 1, 0, 1, okay, which is nothing but 5. Okay, 1, 0, 1, which is 5. Just see here, 1, 0, 1, which is 5. And then similarly, triple 1, 1, 1, 1, okay, which is nothing but 7. Okay, so this is how we get 3, 5, 6, and 7. Okay, addition of similar terms for any number of times is same. Simply we have single term. So addition of, yes, yes, that is true. That is true. Okay, that is true. So uh, 1 plus 1 is always 1, and then you add 1 again, it is 1. Okay, so it doesn't hamper the value of the function. The reason why I'm taking extra terms here is so that I can group them. Why I want to group? So that I want to reduce them, because see, your flow chart has the step where you generate equation, and after generating equation you cannot just keep that equation. Of course you can implement, but it's always good to get the equation reduced, okay, or simplified. Okay, so that's why you have switching equations and equations simplified. So in order to satisfy this, okay, in order to get a simple equation, okay, we add those terms, group them, so that equations become more simpler. Okay. So I think we are clear with these concepts here. Okay, so we have a statement. I draw a block diagram, draw a truth table, I generate equations, and then through equations I try to reduce them, okay, group them, reduce them. Okay, so the next concept is your KMap. Okay, your KMap, which is also called as Karnoff map. I think you would have heard of this term in your basic electronics. Have you studied about KMaps in your basic electronics?
No, sir.
You have not
No, sir.
studied? Okay, fine. So we will go ahead in understanding as to what are these K-maps. Now, just like how we use algebra here, okay, just like how we use equations XYZ here, we use something called K-maps. How does this K-map look? Okay, I will just show you, and it will be easy for you to understand. Okay, so this is how a K-map will look. So does this look familiar to you guys? This particular structure, does it look familiar? It was not that clear. It was not clear. I was not able to get you there. Okay, fine. So this is how your KMap looks. Okay, so we will have to draw it like this and then group them together. Okay, nevertheless, we will try and understand Okay, so this is a most repeated question in your examinations and in your tests. Okay, where we have to go ahead in understanding these K-maps. So 4 bits and 5 bits of variables. Okay, to understand what is a K-map, okay, uh, we first read out. Okay, it's a map which in reducing the complexity of the function. Okay, so just please give me a moment. Are you all able to see my screen? Okay, so K-map is actually used for minimizing a function. Okay, so when I say minimizing a function, which means I have this equation here, big equation. So using my K-map, I can actually reduce it to a smaller form. Okay, so how do I do it? Let's go through the information. The complexity of a digital logic gate that implement a Boolean function is directly related to the complexity of algebraic expression from which the function is implemented. So, just like how we use Boolean algebra here, in the same way we use K-map. Okay, in the same way we are using K-map. Am I audible now? Can someone please respond? Okay,
Yes, sir.
okay. So truth table. Although the truth table representation of a function is unique, okay, these are properties of truth table. Okay, expressed algebraically, appear in many different forms. Okay, that's fine. We can even use Venn diagrams. I think Venn diagrams you would have seen in your mathematics, right? The circular diagrams that we draw union, intersection. Okay, all those which we use in our mathematics. Okay, Boolean functions may be simplified by algebraic means using Venn diagrams. This procedure of minimization is awkward because it lacks specific rules to predict each step in the manipulation process. So Venn diagrams we're not going to use. Truth table also we're not going to use. We will use something called map method. Okay, now this is important. Map method provides a simple straightforward procedure for minimizing Boolean functions. Okay, why are we using this? Can you please note down these 3 lines? Map method, put the heading as map method and take down these 3 lines. Map method provides a simple straightforward process for minimizing Boolean functions. Very important, please note down. So we are using this maps for minimizing functions. What do you understand by minimizing functions? I have a larger equation and I am minimizing this using algebraic way, but this same equation can be reduced using map method. That is what I'm trying to say here. This method may be regarded either as pictorial form of truth table or as extension of Venn diagram. So it is a combination of truth table and Venn diagram. Okay. The map method was first proposed by Rich and slightly modified by Karnoff. So there are two names for the same map. We call it as Witch diagram or Karnoff map. In simple, we also call it as KMap. In simple, we also call it as KMap. Okay. So let us see one simple way of um, representing the KMap. Okay. So we will just see the introduction to KMap in today's class, and tomorrow we will start solving these kind of problems. Okay. So this is going to be our last section for today's class. Two variable map can be done easily using truth table. Okay, two variable means 0 0 0 1 1 0 1 1. So it can be easily simplified using truth table. Okay, how is it using truth table? Just like we did previously here. Okay, yeah, just like we had it here. It's very simple. We take it. Okay, if possible, we try to reduce, or we just put it in the same form because it's very simple. It's only 2 bits. Now, as the complexity increases, okay, as we go to 3 bits, 4 bits, 5 bits, as the complexity increases, okay, you will understand that reducing such equations becomes challenging. See, for example, we had 3 bits here, right, x, y, z. So, using just 3 bits only to reduce, it took us a little extra effort in actually, taking those common terms and repeating them and trying to understand as to how to group them and reducing to our final format, right? So similarly, when we increase the number of bits from 3, 4, 5, so as we increase the number of bits, the complexity also does increase. So that is made simple for us using KMap or Karnoff map. A 3 variable map is shown in the figure. Okay, so this is our figure here and this is our 3 variable. How do I know that it's 3 variable? It's because it has x, y and z. Map consists of 8 squares. Why do we need 8 squares? Because values range from 0 to 7. So if we count from 0 to 7, how many values do we have? We have 8 different values. 0, 1, 2, 3, 4, 5, 6, 7. So totally we have 8 different values. So map will have 8 squares. So let us count them. 1, 2, 3, 4, 5, 6, 7, 8. So I am having 8 squares. The minterms are arranged not in binary sequence but in a sequence similar to reflected in the code or gray code. Okay. The characteristics of this sequence is that only one bit changes from 1 to 0 or from 0 to 1 in the listing sequence. Okay. Now all of you concentrate here. Okay. And we will try and understand as to how exactly this is done. Okay, so first I start off with 0, 1. I don't go with 2 here. Instead 2 is written here and then 3. Okay, next 4, 5, not 6 here, but 6 is written this side and then 7. Okay, now why do we do this? Because I just want one bit change in my binary. Now I will split this as x, y, z. So x is taken here and yz is taken towards this side. Okay, so x, since it is only one bit, it will have two combinations, which is 0 and 1. Yz is 2 bits, so it will have yz is 2 bits, so it will have how many? 4 combinations, 0 1 2 3. So 0 0 0 1, and this is 3, okay, and then 2. Why am I doing this is because, okay, let me try to use the tools and we will see if, okay, now 0 0, okay, 0 is already here, okay, 0 is already here, okay. Now if you can see, there is only one bit change, 0 and 1, so there is only one bit change, isn't it? So this 0 and this 1, so there is only one bit change here, right? So why am I doing this is just because I need only one bit change, okay. Now let us consider, okay, let us consider um, the next terms now, okay, the next terms. Now 1 is here, okay, I have 1 even here, but then there should be only one bit change, so 0 to 1, the other bit should be the same. That is why instead of having here as 2, I am having 3, okay. So was this concept clear for you guys? Why we are trying to have 3 and then 2? Was it clear? Please respond. Was it clear?
So could you explain once more, sir?
Once again, okay. Now I have 0 here, okay. I have 0 also here, so this bit remains the same. I need only one bit change, so that bit change is happening with the second bit here, okay. So what is that second bit here? Second bit is nothing but my 0 and 1, so only one bit change. So if you compare 0 0 and 0 1, there is only one bit change, right? Because these zeros remains the same, and this 0 and 1, so only this second bit has changed, so which means there is only one bit change, okay. So all that you have to keep in mind is that your values, okay, should actually start 0 1 2 comes here and then 3. Say for example, if I keep 2 here, okay, let us compare this, and you'll be able to understand as to what is happening, okay. Now let us compare this and this here, okay. 0, okay, 1, so I have one bit change, and then here I have 1, and then I have 0. So is there a one bit change here between these two? Please respond. Please respond. Is there a one bit change between these two?
Yes, sir.
There is more than one bit change, right? There is more than one bit. But what is the rule? The rule is that I should just have one bit change. But here the first bit is also changing. 0 and 1 is also changing, right? See, you can see this is also changed. This is also changed. And then you can see this is also changed. And so we do not need many changes. We just need one bit change. So that is why instead of keeping it here next to it, okay, instead of keeping it here next to it, what I do, I actually keep it here. This is where I keep, so that I will have just one bit difference, okay. So we will try and understand this in the next class, okay, and we will see exactly as to what can be done, okay. We will get back with this explanation again tomorrow. So whatever I explained to you all, was it clear so far? Did you understand why we are trying to put 2 here and then 3 here? Yes? Okay.
Yes, sir.
Yes. So tomorrow we will revisit this concept, okay, and we will try and understand as to how we can do this. Okay. So I think we will end the class now, and we will revisit these concepts again tomorrow. Okay. Fine. Thank you.